bet.
Okay.
Coordinate systems and phasors and real, let's see, rectangular and polar coordinates. I think this is a short paragraph.
We've got a bunch of guys in the room, so being coordinated, yeah.
Huh?
Bunch of guys in the room being coordinated, that's not gonna be a big topic.
Okay. I don't know why we got that green ball. Okay, so we normally plot impedances on a rectangular coordinates. If we plot them in polar coordinates, we plot the length of the vector, the magnitude, which in this case is we're showing it as R, and the phase angle, either a positive or negative phase angle. So in rectangular, to plot point P, it's somewhere along the X coordinate, somewhere along the Y coordinate. This is kind of redundant, but we normally plot the real part of impedance along the horizontal axis and the imaginary part or reactance on the vertical axis. Inductive being positive, capacitive being negative. So what coordinate system do we often use to display resistive, inductive, and or capacitive reactance components of impedance?
Hey, wait, the right answer isn't on the screen. It should be nano DNA. Right.
Part of this is cut off on the screen. I can't see the whole page. I don't know if it's just me or.
That's what that box is.
That's
The
what's,
green box is showing what they see.
what's being shared.
Who put the green box
Since
up
we didn't
there?
talk about any of the other three.
Yeah.
It's on the green box. Oh, there you go.
Yeah, but I got to get back to the
Sharon.
share. That's the problem.
Yeah, you're 90 degrees out of phase, Bob.
Right. Start the share. I'll check these just for sure. We want, let's see. All right. Yeah, what is what this?
It went outside the box.
I think we've got to share it from this screen rather than before.
Yeah, here.
In the window side.
Escape out of this real quick.
So
Let me see if that's up.
Already up to about 50%.
Okay. Here,
I see a green now.
where's your display here?
Yeah, look at extra study lives through the years that it's sent on the show. We should always like be miles.
Oh, yeah, displays. We want to extend these displays.
Okay.
All right, so 2 is now where your slideshow is.
All right.
So open,
yeah,
is this where we're at?
Yep.
So we're gonna drag this over to here and maximize it and start the show from here. And then share it.
I've been.
And when you share it, you're gonna share this screen.
All right. Good. While you're here.
Drag the mouse back over. So we're gonna stop share.
I really start.
Screen 2.
Okay.
Share.
Okay.
Okay, so now this toolbar will be up here on your
Okay.
first screen. And then start the slideshow up here. Because you're sharing that screen in entirety.
Oh, okay. So I have to watch it there. Then.
Yeah, if you double click on the top of the toolbar, it should maximize or yeah.
Like someone, I'm there, I'm really. What's that?
All right.
Can you see it now?
Yes, thank you.
Thank you.
Hey, guys.
We got a class in there. It's not.
My friend is. That's all it does.
But you got delta, right?
Yep.
When using rectangular coordinates to graph impedance, what do the axes represent?
Hey, isn't it?
Let me say alpha. Oh, the x-axis, yeah. Of course.
We have any votes for delta?
Alpha.
Let's go with alpha.
Yay,
Resistance
alpha.
on the X and reactance on the Y. What is the impedance of a pure resistance plotted on rectangular coordinates? Oh, excuse me. Where is the impedance? Wonder about that. Plotted.
Doggy.
Only horizontal axis. Okay, these are hard ones. Which of the following represents capacitive reactance in rectangular notation?
Let's see. Yeah.
Negative, imaginary. What does the impedance 50 minus J25 represent? You throw two of them out right away, right?
50, first one low.
50 ohms.
We don't think it'll be.
And then imaginary.
It's positive.
Minus
25 is, or is that negative?
It's
Minus.
Minus.
So it's capacitive.
So it would be B.
B sound good. If the impedance was 50 plus J25, it would have been 50 and 25 ohms of inductive reactance. So, how do we find impedance? We can plot the inductive reactance on the positive Y, the capacitive reactance on the negative Y, and then figure out what the difference is. And then plot the resistance on the x-axis, and draw your vector for the magnitude of it. Use Pythagorean theorem to find the length or the magnitude of the impedance, and then do the arctangent. In other words, find the phase angle. If you're trying to do it in
I like Rick's answer better.
which answer?
Username of VNA.
Okay. So when we plotted it, when we plotted P, when we did the resistance on X and the reactance on Y, we came out with a vector and an angle. In this case, the resistance part of it is the magnitude of the impedance times the cosine of the angle. And that's important because we're going to talk about power factor. So in polar coordinates, we see the magnitude and the phase angle. So a positive phase angle means it's inductive, and a negative phase angle means it's capacitive. And we use phasor diagrams to show the phase relationships between impedances and resistances for given frequencies. So what coordinate system is often used to display the phase angle of a circuit containing resistance, inductive and capacitive and/or capacitive reactance?
Doggy.
Does everybody know what a Maidenhead grid is?
No,
Worldwide chart of, on the map.
Yeah.
Yeah.
It's the world divided up into geographical locations, and they designate it by 2 letters, 2 numbers, and 2 more letters if you do the whole 6.
Box.
Alright, so that's the grid on my map,
Covered in
on my wall here.
Okay? What? Oh. How are impedances described in polar coordinates?
Let's say, yeah, Charlie.
State by phase angle.
Phase angle and magnitude, length of the vector and the angle. Which of the following represents an inductive reactance in polar coordinates?
Oxygen.
Sort of.
How we tell the difference between inductive and capacitive reactance is what? The phase angle, right?
Yeah,
Positive phase angle.
yeah, possibly.
What is the name of the diagram used to show the phase relationship between impedances at a given frequency?
Phaser, see,
A phaser. That's all you have to know about phasor diagrams. Which point on this chart best represents the impedance of a series circuit consisting of a 400 ohm resistor and a 38 picofarad capacitor at 14 megahertz? So you need to figure out what the reactance is of that capacitor at 14 megahertz.
First thing I do is what quadrant,
That's a negative.
you can tell which of the 4 quadrants right away. Question.
I mean, and you know, the horizontal at 400, you know,
So resistor is
you
X,
know that point.
picofarad is positive or negative?
negative.
Negative. So it's in the bottom right quadrant, and you got down to 2 points right off the bat. So now you're just looking at magnitude.
Actually, you only have one.
Yeah.
At 400.
I know, yeah, process of. Right there.
Or you do it with your calculator and find out what that point is, and it's close to 400 negative. 300 negative. Now, odds are you're going to get one of these because there's a number of these. So now we have 300 ohms and an 18 microhenry inductor at 3.5 megahertz.
Let's we plot the 300.
So, yeah, we know
And it's positive. So that's gonna be either. Three. Yep.
somewhere around here, right? One of these 3
Mm-hmm. That's to be 3 or 8. But it's micro, which is.
positive. So it's one of these 2. So you got to figure out approximately what the reactance is going to be.
Microhenries isn't a lot. So we'll say 8. But.
So if you do it on your calculator and do the 2 pi FL, you should come up with 396.
Hmm.
Ooh, 2.3.
Okay, so now we got a 300 ohm
I got
resistor
one
and a
ohm.
19 picofarad capacitor at 21.2 megahertz. At least they are picking frequencies in the hand bands.
Well, it's a capacitor, so it's gonna be negative, right? So 0.1.
Yeah.
This one will be 1 point.
Yep.
We have to figure out what one.
300, 300, looks like you don't have a big choice there.
Yeah.
You don't need a calculator for that one.
That's awesome.
Okay. So, I'm sorry you're gonna get one of those for
Charts we run on the test.
Yeah, except they won't have the arrow put in.
No.
So on that one, you just stop no recording by FL.
Yeah,
Right. You would go.
But that's,
Huh?
I don't know how you stop it.
We have to get to the
next time.
All right, thanks.
You doing?
I'll send you the YouTube link
Yeah, if you send me YouTube links, I'll watch them later.
and I'll put the charts on Dropbox.
Okay.
Send you a link to that.
Okay, thank you very much.
Okay.
We're good.
I'll see you next time.
All right. Where'd my mouse go?
Oh, wait a minute. I saw it just a second ago. Try again.
So I just take.
Oh, there we go.
G8X. I think, or